Good evening to you all. Am I audible, everybody? If you can hear me, please send some highs. Navraja, we make videos in English only. Actually, in Biotechnica, you will see all the videos, all the shorts, everything we make in English. So I don't know whether you have seen the correct all the videos from Biotechnica or not. We specifically do it in English itself. All our live sessions are also completely done in English. Welcome to the session, everyone. I can see 6 people. Yes, can I have some highs from everybody? So let me introduce myself. My name is Tithi, as you know, and I will be taking this session. And in this particular session, we'll be talking about a very important topic from Unit 8, that is inheritance biology, pedigree analysis. Now, pedigree analysis is one of the section from where questions do come every session. And the questions which come usually they come in part C only. So this is a part C specific topic, and also the question pattern from pedigree analysis, yes, that is constant. Like questions do come. What has changed, okay, is the pattern of question that comes from pedigree analysis. So as we go along in another 1 hour, where we'll be discussing some difficult part C questions, and I will be giving you tips and tricks of how to solve them also. I want all of your uh, continuous participation, interactive participation, then only it will be fun. Okay, so I'm not going to judge you, I'm not going to score you. So when I'm showing a question, I want you all to try to solve it. I'll be giving you 2 minutes, everyone, to solve it and give your answer, and so that we both can have fun. Okay, so it should not be like a monologue. So here, not only I will show you how to solve the question, but before that I want you to try as well, because what we believe in Biotechnica is ultimately, like, that is the ultimate truth also, that all the faculties of Biotechnica can just show you the door, but it is you only who has to open the door and enter through it. Okay, so it's you only who has to write the exam. So it is very important that you are able to solve those questions in the exam hall. All right, so for that you have to try. I will help you, giving you tips and tricks, but you have to try as well. All right. Can I have some responses from everybody? Can I have some thumbs ups? Are you all ready for this session for next 1 hour, where we'll be discussing pedigree analysis related questions? Please respond. See, without your response, it won't be even fun. Even a single person, if you are not responding, it won't be fun. So please respond. All right, let's get started. So the very first question is here for you. Okay, so this is a question that came in one of the recent past sessions of CSIR exam. So that is what I was telling you, that earlier the questions that used to come from pedigree analysis, so they used to have bigger pedigree charts where there were 3 4 generations information was given, and also questions related to inheritance patterns, like you have to detect the inheritance pattern. Along with that, you also have to calculate the probability of a particular trait to be seen in a generation or in an individual. So those kind of questions were more frequently asked. However, now what we see is that the trend has changed. Now those questions, yes, they still do come, but along with that, one thing that is constantly coming in all the sessions is a shorter pedigree chart. Okay, not involving 3 4 generations, maximum 2 generation pedigree chart. Along with that, they are giving the molecular marker data. Okay, so every pedigree question in the recent sessions, if you see, they are associated with some or the other molecular marker data. Okay, so it is very very important, guys. I'm telling you once again, molecular marker is a topic in unit 13. Along with that, molecular marker is also there in unit 8 as well, because it is a part of physical mapping. But along with that, all other things, like whether you're talking about mutation related questions or this one pedigree related questions, always, or even Mendelian inheritance pattern related question, in all of those things, molecular marker associated data are for sure coming in the exam. Okay, so the questions, it is always associated with some or the other molecular marker associated data. So make sure that you understand molecular markers very good, and also make sure that you know how to decipher the data. Okay, you know how to comprehend the data, how to make sense of the data that is given here. All right, so this is the first question. So guys, if you are like, this is just tip number 1, that if you are uh, lacking, or if you have any kind of doubt in molecular markers, this is the time to get it cleared. Okay, because lot of questions we see nowadays which is associated with molecular markers. So molecular markers is something that should be completely solid with you. Okay, so the concept as well as how to comprehend the data given. All right, so let's see this question, everyone. Okay, I want you all to try. I'm giving you 2 minutes. So pedigree in panel 1 represents the inheritance pattern of a given trait. The trait is not 100% penetrant. Panel 2 represents PCR amplification profile for each member of the family using a specific primer pair. M for mother, F for father, and C for child. So panel 1 shows the pedigree chart, and panel 2 shows the molecular marker data. What is the mode of inheritance of this trait? If you have solved, please give me your answer in the chat box. Please type in your answer. Anyone? Did you solve? Navraja, are you there? Would you like to answer this question? Let's see this question here. So panel 1 represents the inheritance pattern of the given trait. Okay. And what is very important that is mentioned in the question is that the trait is not 100% penetrant. Okay. So here you should have the understanding of this concept of penetrance also. Now, if a trait is 100% penetrance, means whoever is there with the related genotype, they all will show the phenotype. But when a trait is not 100% penetrant, means even though there is an individual in the population with the related genotype, but the expected phenotype will not be there. Okay, so that will happen if the trait is not 100% penetrant. Okay. Right. Now, what is the benefit of using molecular markers is that even like when we are looking for the traits, okay, the phenotype of the trait. So phenotype can be there or may not be there when the trait is not 100% penetrant. So it is not 100% penetrant. So there might be individuals who have the genotype, but still the trait is not produced. Okay. Now what happens is when we are looking for at the molecular markers, now molecular markers are associated with that particular trait. Okay. So molecular marker will show us whether the individual has that particular trait or not, even though phenotypically it is not produced. Okay, so this is the advantage of using molecular markers for genetic for the detection of genetic disorder, that if you have a molecular marker that is associated with the with the mutant allele or the allele which is responsible for the disease, so even before the disease is showing a phenotype or the disease is showing symptoms, before that also you can detect by the by analyzing the molecular markers, because marker will be there. Okay, if the person has that particular genotype, the marker will be there. Okay, so when we have a look at the markers here, okay, so what we see here is in family 1 the mother is affected, right? So mother has this particular pattern where she has 3, 2 and 0.5 kb bands. One in family 1, father and son are not affected, so both of them don't have this particular 3 kb band. Okay, now similarly in family 2 also, if you see this two individual like father and daughter are affected, and both father and daughter has this 3 kb band. Okay, so from this two analysis, what you can associate, that this 3 kb band is associated with the disease. Or let's say trait here, because we don't know whether it is a disease or not. So this 3 kb band for sure is associated with the trait. Okay, so in family 3, whoever has this 3 kb band should have the trait. Okay, so here you see in mother and child has this 3 kb band, and but what do we see, that mother do not have the 2 kb band. Okay, and mother is not showing the trait as well. Okay, but what it means that, but still mother has the 3 kb band, means she has the mutant allele, but the trait is not produced, or the phenotype of the trait is not produced, because the trait is not 100% penetrant. Okay, that might be the explanation. So mother has it. Okay, now when you look at the inheritance pattern, what do we see, that every affected child, so this is an affected child, this is an affected child, they have it, or they have one affected parent. In this case mother is not affected, but we know that mother has the 3 kb DNA band which is associated with the trait, but still she is not producing the phenotype. But because this 3 kb band is there, so the chances also, what has happened, that the child in family 3 has received this 3 kb or the mutant allele producing this 3 kb band from the mother. Okay, so in both of this family 2 and 3, we see that if an affected individual has an affected parent. Okay, and also what other thing we see is that the individual, the in the next generation, whoever has the trait, so there only a single copy is there of 3 kb. Okay, and that is enough to produce the trait. Okay, and also if you see here in family 1, mother is so here we see that mother is affected, father is not, and child is also not affected. Okay, so if we consider that it is a recessive trait. Okay, now first let's consider, so we have to check for all four, right? So let's see whether it is X-linked or autosomal. Okay, now for X-linked, what do we know, that the if it is present on X chromosome, then the males, they will have a single copy only. Okay, but what do we see, that males are having two copies. How do we know males have two copies? Because in family 3, child is a male. Okay, so child has this allele also and this allele also. Okay, the mutant allele as well as this one. All right, so since there are two copies of the allele is present for this particular gene, so definitely this gene is not present on X chromosome, it has to be present on an autosome. Okay, so we can eliminate option 3 and 4. Now for this, so now we have to decide whether it is autosomal dominant or autosomal recessive. Okay. Now this particular situation would have been good to show us that it is autosomal recessive if the, because both the parents are not affected. So if both the parents are heterozygote, then they won't be affected, and then there is a chance of producing homozygous recessive. Okay. But what do we see? This molecular marker data which is given to us, it's showing that mother has the mutant allele. Okay, it's not that mother does not have, mother has the mutant allele, and because mother has the mutant allele, so this situation homozygous recessive is not there. Okay, so all the offspring is getting that particular causative allele from the parent, and if it is getting from parent even a single copy also, that is making it affected. Okay, so the conclusion that every affected child has at least one affected parent, so it is pointing towards autosomal dominant. Okay, so answer will be option 2, not autosomal recessive. Okay, so this was the catch here, that without analyzing the molecular data, if you have looked directly in family 3, you will automatically say that it is autosomal recessive, right? Because parents are not affected, but child is affected. But when you analyze the molecular data, then you see that even though phenotypically mother is not showing the phenotype, but mother has the causative allele. Okay, and this also is supported by the information given in the question that the trait is not 100% penetrant. Okay, so the answer will be autosomal dominant. Did you all follow? All right, moving on to next question. This also, you see, is again, we have to use the information or pedigree analysis, or how the traits are passed on from one generation to another, or parents to offspring. But along with that, we also, the data that is there, okay, it does not include any pedigree chart. It includes the markers which are present. Okay, so SNP is a marker, that is single nucleotide polymorphism. STR is short tandem repeats. Okay, and they all are molecular markers. So polymorphic DNA sequences are used for molecular identification. Short tandem repeats, STRs and SNPs, are used as polymorphic markers. The table below summarizes the status of autosomal SNP, autosomal STR. So autosomal SNP and autosomal STR are SNP and STR which are present on autosomes. Mitochondrial SNP means this SNP is present in mitochondrial DNA, and Y-linked STR means this STR is present on the Y chromosome. Okay, representing so there are 4 individuals ABCD. Out of that, 2 are parents, 2 are children. Based on the above data, identify the individual representing 2 parents. You have to decide who all are parents here. Yes, I'm giving you 2 minutes. Try to solve it and answer. Yes, anyone? Okay, so let's have a look at this question and see how to solve it. Okay, so we will start with the Y-linked STR. Now, Y-linked STR, as I told you, means it is present on Y chromosome. Now, who all will have the Y chromosome? Only father and son. They only are males and they only will have the Y chromosome. Mother and daughter will not have. Okay, so from this information itself, without doing any kind of analysis, you are for sure know that A and B are males and C and D are the females. Okay, so males means it will be father and son, females means mother and daughter. Okay, now moving on to mitochondrial DNA. Now, what is the characteristic of mitochondrial DNA? Mitochondrial DNA shows maternal inheritance. Okay, what does mitochondrial DNA do? It shows maternal inheritance. What do we mean by this? That maternal DNA in the zygote will pass from only mother. Okay, so mother will give the mitochondria to the zygote. So irrespective of whether the zygote is going to develop into male or female, the mitochondria in the zygote is coming directly from mother. Okay, so whatever marker that we are looking for in the mitochondrial DNA in mother and both the offsprings is going to be same, because both the offspring, son and daughter, will receive it from the mother. Okay, now if you now see SNP1, so SNP1 is only given here to confuse you, because SNP1 there is no change. All four individuals has C at this particular position. Okay, so it is not having any change, so we cannot analyze it. If it is all same, we cannot analyze. We have to analyze the polymorphism. Okay, that is when it is present differently. So what we see in SNP2 is individual A has G at the particular SNP2's position, but BCD has A. Okay, now this is the SNP which is giving us information. So what did I tell you? That mitochondrial DNA shows maternal inheritance, means mother and both offspring, son and daughter, will have same marker. Okay, so marker will pass from mother to both son and daughter. Okay, so from here what do we know? That BCD will be for son, mother and daughter. So that means A will be what? Who will be A? Individual A. So there are only two males, A and B. Out of that, we know for sure that B is son. That means A is the father. So individual A is father. Okay, that much we have known. So when we know that, so automatically you can eliminate option 3 and 4. Okay, now this is another tip I would like to tell you, that I myself find this kind of this way of solving question is better, where you solve the question in part and do the sequential elimination. Okay, so that you can narrow down to your answer faster. So we know that A is father. Okay. Now out of C and D, who will be a mother and who will be daughter? So now we have to move on to the autosomal markers. Okay. Now in case of autosomal marker, when we see the STR, okay, STR, what we see here is that both C and D has 13 and 14. Okay. Now, A is father. So, whoever is daughter is going to get one marker from mother, one marker from father. Okay. So, just because 13 is a marker which is present in all. All right. So, it is possible. So, it is possible that 13 in the child is coming from either, it can come from either of the parent. Okay, now because okay, so out of C and D, both are females, both have 113 and 114. So 13 for sure is coming from father A, that means 14 is coming from mother. Whoever among C and D is mother, so 14 is coming from mother. Okay, but still we can, this information does not give us any clue about who is the mother out of C and D. Okay, so let's check this SNP, the autosomal SNP. Now, in autosomal SNP, we see here is that uh, individual C is homozygous recessive. Okay. Now, individual A is also homozygous recessive for C. Okay. Now, B, we know that B is son. Okay. Now, son for sure will get one allele from father, one allele from mother, right? So here, son has C. So C can come from father or mother, right? Because A, C, and D, they all have this CLE. Okay. But individual B, who is the son, also has an SNP G at that particular position. Okay. Now, G is for sure cannot come from father because father does not have G, but father is homozygous for C. Okay. Now, that means G in son is for sure coming from mother. Okay. So, out of individual C and D, who could have given the G allele? Only individual C, because individual C only is heterozygous for C and G. D is homozygous again for C, right? So this means individual C is the mother. Okay. So who are the parents? Father and mother. Who are they? A and C. Okay. So you can eliminate option 1, and your option and the correct answer will be option 2. Okay. So as you can see here, even though the information is not like the pedigree chart is not there, still we have to analyze the question keeping in mind the inheritance pattern of the different traits. If it is present on mitochondria, if it is present on autosomes, if it is present on Y chromosome, how the traits are passed on. Okay, now before we go ahead, very important announcement that we are Biotechnica is going to start Lakshya batch from tomorrow onwards for CSIR NET 2025 as well as for GATE 26 exam. So if you enroll for this batch, you get this molecular biology hands-on technique and internship program completely free with your subscription of the course for 1 year. So as you know, all know that Biotechnica's classes has many benefits. So you get the recorded sessions also. You get 24/7 chat support. You get dedicated study portal. You get the Conceptica series, many other revision things. You get the access for AIMNet exams, that is the mock test for CSIR NET exam. Okay, so along with that, I'll tell you that only very few features are mentioned. So please, you can check out our Biotechnica store, or you can call in this toll free numbers. You can contact us in this toll free numbers to get more information on Lakshya batch. So guys, if you are targeting for CSIR NET 2025, the June one or next one, or the next to next one, okay, so please enroll for Lakshya batch. That will definitely help you in clearing your target. Okay, moving on to the next question. So again, you see, this is also a question which was which came in a past recent session exam, and again here you see that there is pedigree chart associated with the molecular marker data. Okay, see guys, you have to be very much clear about this understanding of the molecular data. Okay. All right. Next question. So this is a hypothetical example. The pedigree of a monogenic trait is given below. The shaded individual show spotted skin color while the rest have uniform skin color. The individuals 1 to 9 in the pedigree were analyzed for a DNA marker that shows complete linkage with the skin color trait. The following statements were made regarding the above observations. Okay. Now, again, here, as I told you for the previous question also, that even though an individual is not producing the trait, but if the individual has the potential to produce the trait, means if the individual has the causative allele, so that will show up in the molecular marker data. Okay. So when we are having this kind of questions, so our first job will be to associate the trait with a particular molecular marker band. Okay. Now, what we see here is individual 1 is affected, 6 is affected, 7 is affected. Okay. So now let's check out the band pattern of 1, 6, and 7. So as you see, 1 has this 2 bands, 6 also has 2 bands, 7 also has 2 bands. Okay. So what does it tell us? That if an individual has the potential to produce the trait, so that particular individual will have the 2 bands. Okay. The individual who are not affected, as you see here, they have only single bands. Okay. Now, at the same time, we see two individuals, individual 3 and individual 5, who have 2 bands, but still they are not affected. 3 and 5, they are not affected. Okay. So they have 2 bands, which ideally should make them have the trait. Okay. So this particular spotted skin color, so individuals, so what is the band pattern for spotted skin color? So we see that spotted skin color, the individual who have the potential to produce spotted skin color will have 2 DNA bands. Okay. So individual 3 and individual 5, since they have this 2 DNA bands, so they should be having spotted skin color. Okay. But still they are not showing the phenotype. What does it mean? That this particular trait is not 100% penetrant. Okay, so again, what do you mean by penetrant? That there will be individuals in the population who has the potential to produce the trait, but still they do not produce it. Okay, so the following statements were made regarding the above observation. Spotted skin color is a dominant phenotype. Okay, so is it a dominant phenotype? What is the characteristic of dominant phenotype? That it will, so it will never happen that the individuals have the trait, but none of the parents have it. Okay, affected individual always have at least one affected parent. Okay, so we see that individual 6 and 7, they have these 2 bands, and individual 3 also has 2 bands, even though she is not producing the trait phenotypically, but molecular marker is showing that she has 2 bands. Okay, means the second band in 6 and 7 must have come from 3 only. Okay, so 3 only is passing. So and 4 doesn't have this second band, right? Means only a single copy of this second band is coming, or the heavier band is coming in individual 6 and 7, and still they are getting affected. Means it is a dominant phenotype, because that is the characteristic of dominant traits, right? That even though they are present in a single copy, the trait will be expressed. Okay, so that means it is a dominant phenotype. So with that, your statement A becomes correct. Okay, now as I told you, as you see, as you are confident that statement A is correct, immediately look for the options. So in option, you see option 3 and 4 doesn't have statement A, so you can eliminate it. Okay, now statement B says that spotted skin color shows variable expressivity. Okay, so this is not variable expressivity. Variable expressivity would have been, so there's no information given in expression level of the trait in the affected individual. Okay, but from the data that is there, what we have concluded that it is not 100% penetrant. Okay, so it is not complete penetrance, but there is no information about expressivity. So when we look for penetrance, we have to analyze the entire population. So there will be individuals in the population who has the potential, means who carry the mutant allele, but still the mutant phenotype is not produced. Expressivity is detected in an individual only, at the individual level. That the so if there is a different level of spotted skin color, like some individual have highly spotted skin color, some individual have mildly spotted skin color. Okay, that would have been variable expressivity. But because no such information is given here, so we don't know about variable expressivity. Okay, so statement B is incorrect. Now with this much information only, if you check the option, what you see, that option 1 can be eliminated. Option 1, how it can be eliminated? Because B is incorrect. Okay. So if B is incorrect means A and C. So you have already got your answer, which is option 2. Okay. But we will see as well why statement C is correct. So the DNA marker associated with the skin color trait is codominant. Okay. Now, what is the feature of codominant molecular markers? That it will show a band pattern that will be different in homozygotes and heterozygotes, right? That is the feature of codominant markers. So here in the in this particular molecular marker data, you can see that the individuals who have single band means they are homozygotes. Okay, whereas the individuals who have the double bands, they are heterozygotes here. Okay, so because it is showing different band pattern for homozygotes and heterozygotes, so it is a codominant marker. Okay, so C is correct. Now statement D, what it says. So you already have got your answer. Okay, but let's see statement D also. The probability that the individual 5 will pass the allele responsible for the spotted skin color to the next generation is 0.25. So who is individual 5? This person. Individual 5's genotype is what? That two different bands are there. Okay, so if we say that because we have established that it is the dominant phenotype, so that let's say that this is caused because of gene A. Okay, so capital A is associated with this band, small a is associated with this band. Okay, so individual 5 has both the bands, means genotype of individual 5 is capital A small a. So if the genotype of individual 5 becomes capital A small a, then in the next generation, what will capital A small a do? It will produce two different type of gametes. Half of them will have capital A, other half will have small a allele. Okay. So this capital A allele, if it is passed on to the offspring, they will have the spotted skin color. Okay, so what is the probability that 5 will pass it on to the next generation? So that will be the probability of passing capital A to the next generation will be 0.5. Okay, because 50% of the gametes will have capital A. Okay, it is not 0.25, it is 0.5. All right, so with that, statement A and C only are correct, and answer is option number 2. Did you all follow? All the students who are attending, please give some response. All right, moving on to next question. So the pedigree below is in reference to Angelman syndrome, which is caused by a mutation in UBE3A gene on chromosome number 15. The gene is also paternally imprinted. Individual showing AS has not been indicated in the given pedigree. Individual 1-1 does not have AS. Individuals marked with dots are carriers for UBE3A mutation. Which one of the following options lists individuals, all of whom are likely to show AS? Now, for this particular question, you have to have information on this Angelman syndrome. Okay, see, in your CSIR syllabus, there is a topic for genetic disorders in humans, right? So you have to have information about the genetic disorders and how that is caused, or how that particular disorder is inherited. Okay, because here the pedigree chart is simple, but if you don't know what is Angelman syndrome, how it is inherited, then it will be impossible for you to solve this question. And at the same time, if you have even little bit idea about also Angelman syndrome, you will be able to solve it. Like, it's my guarantee you will be able to solve it in less than 30 seconds. But you have to have this basic information about Angelman syndrome. Okay. So, what is this Angelman syndrome? Let's have a little background on that. Angelman syndrome is a genetic disorder which is caused, as it is mentioned here, it is caused by a mutation in this particular gene which is present on chromosome number 15. Okay. Now, especially it is a deletion. So, a deletion happens in this particular segment in chromosome number 15. Okay. And that results into Angelman syndrome. Now, just like Angelman syndrome, there is another syndrome which is called as Prader-Willi syndrome, which is also caused by a similar deletion in the similar location of chromosome number 15. Okay. Now, what is the difference in both of them? Definitely, they have some different symptoms associated with it, but excuse me, genetically, what is the difference in them? So, what we see is that this segment is also imprinted when it is coming from a parent. Okay, now what is imprinting? What is genomic imprinting? Imprinting means that a particular segment is tagged or marked for making it silent. Okay, so genomic imprinting, it's an epigenetic phenomena by which the expression pattern of different genes are controlled. Okay, it is one of the epigenetic phenomena. All right. So what we see is that when this particular deletion is inherited from mother, when it is inherited from mother, then it results into then it results into Angelman syndrome. Okay, if this deletion in this gene in chromosome number 15 is inherited from mother, then it results into Angelman syndrome in the offspring. Okay, but if this deletion is inherited from father, then it results into Prader-Willi syndrome. Okay, now what do you see? The chart is easy. You don't have to find out who all has the deletion. It is already mentioned that who all are having the deletion, right? So whoever are carriers of the mutation is already mentioned. All these individuals who are having a dot within them, they are individuals having the mutation. Okay, so from here, what you have to find out, who all are likely to show Angelman syndrome. So you have to basically find out who all are getting this mutation from their mother, because if they are getting from mother, then only they will have Angelman syndrome. If they are getting it from father, they will not develop Angelman syndrome. In that place, they will have Prader-Willi syndrome. But the question is not about that, so we don't have to find that out. Okay, so our target will be to find out who all are getting particular mutation from their mother. Okay, so you see, third generation. So, and it is also clearly mentioned that this individual does not have Angelman syndrome. Okay, because we don't know the information about his parents. Okay, right now in generation 2, both 2 2 and 2 5 are getting the mutation from father. Okay, so will they be having Angelman syndrome? They are getting it from father. So definitely nobody from second generation will have Angelman syndrome. Okay. What about in third generation? Now in third generation, 3 1 and 3 2 are getting the mutation from their mother, who is 2 2. Okay. So 3 1 and 3 2 can have Angelman syndrome. All right. But what about 3 5? 3 5 is getting it. 3 5 is a female, but she is getting it from father. So will she have Angelman syndrome? No. Okay. Now what about in fourth generation? Now again, 4 2 is having mutation and she is getting it from her mother. Right? Means she also will have or she has the potential of producing Angelman syndrome. So who all are likely to show Angelman syndrome? It will be 3 1, 3 2, and 4 2. So answer will be option B. Okay. Moving on to next question. Now, this is a type of question which used to come very frequently earlier in CSIR NET exam, which in which a pedigree chart will be given, and you have to find out the mode of inheritance, or you have to find out the probability that a particular individual will be affected with the trait. Okay, so a 3-generation pedigree of a particular human trait is shown in the following figure. So there are two associated questions. First is, what is the probability of 3 2 is a carrier? So who is 3 2? This is 3 2. right? So you have to find out what is the probability that 3 2 is a carrier. And next thing you have to find out that if 3 4 and 3 3 marry, what is the probability that the first child will have the trait? Means if 3 3 and 3 4 marry, what is the probability that their child will have the trait? Yes, 2 minutes I'm giving you all for your analysis. And everyone, I would like to tell you we are 15 minutes more in this session. And I would like to tell you all that there is a surprise free gift for everyone who attends the session till the end. So, everybody, please attend the session till the end if you want to get the surprise gift from Biotechnica to you all. And I promise you that this surprise gift is going to help you in your exam preparation for this coming February exam. So everyone, please stay there till you get the still stay there till the end for this free gift. You will be able to get the free gift only when you stay till end. All right, so let's have a look at this question. So, what is the probability that 3 2 is a carrier? Okay, now for that, first of all, we have to find out what is the inheritance pattern of this particular disease. Okay, now what we see here is in both the generation 2 as well as generation 3, parents are not affected, but they have a child who is affected. Again, parents are not affected, they have a child who is affected. So, which is possible in case of autosomal recessive only, right? So which means that this particular trait is autosomal recessive. Okay, now once you have deciphered that it is autosomal recessive, now what is the probability of 3 2 to be a carrier? Okay, so 3 1 is affected, means again, let's say that it is gene A, which has two allele, capital A which is dominant and small a which is recessive. So the genotype of 3 1 will be small a. If 3 one's genotype is small a, what will be the genotype of 2 1 and 2 2? So 2 1 and 2 2 have to be heterozygous, right? Both of them have to be heterozygote. Now, if both the parents are heterozygote, so in the third generation, what is the probability of 3 2 to be a carrier? Okay, so what is the probability of 3 2 to be a heterozygote? Okay, so what it will be? So for that, you have to do a Punnett square of the parents. So parents are heterozygote here. Okay. So what are the possible genotypes that we get in the next generation? This is it. Okay. Now out of that, because it is homozygous autosomal recessive, so this individual will be affected. Okay. But what about this portion? They will be normal or not affected. Okay, so in this normal progeny, so when there is a cross between two heterozygotes, so among the normal progeny, what do we see? 2/3 of the individuals are heterozygote, whereas 1/3 are homozygous dominant. Okay, so our question is to find out what is the probability that 3 2 is a heterozygote. So, what will be the probability? Because 3 2 is a normal progeny of these two heterozygous parents. So, chance of 3 2 to be heterozygote will be 2 by 3. Okay, so A's answer is 2 by 3. So, when you have A's answer as 2 by 3, as you check here for the options, so option 2 and option 4 are eliminated. Okay, now the second part says that if 3 3 and 3 4 marry, what is the probability their first child will have the trait? Okay, now for their first child, or to find out this probability, we first have to identify the genotype of the parents here. Okay, so who are the parents of the fourth generation? 3 3 and 3 4. Okay. Now again, 3 3 is also a child of two heterozygous parents and normal. So probability of 3 3 to be heterozygote. So probability of 3 3 to be heterozygote will be how much? Just like how we have calculated for 3 2, it will be 2/3. Okay. Now what was the genotype of 3 4? So you see, 2 3's genotype is small a small a. 2 4's genotype is normal, so we can put capital A and dash. Any allele can come and take the place. Okay. Now, for fourth generation, in the third generation, in 3 4 is normal. 3 4 is normal means 3 4 has one dominant allele. Okay. So from where 3 4 is getting dominant allele? For sure from her father. Why specifically from father? Because mother do not have any dominant allele to give. Okay. So if father is giving this dominant allele, so one allele will come from mother also. Now mother of 3 4 is affected. So 2 3, who is the mother of 3 4, can only give a small a allele. So what allele 3 4 is getting from mother has to be a small a. Right? So if 3 4 is getting a small a allele, means automatically the genotype of 3 4 is heterozygote. Okay, there is no probability associated here. Like if you have to calculate the probability of this will be 1. Okay, means because for sure 3 4 has this particular genotype only. Okay, for 3 3 it can have two different genotype. It can be capital A or capital A small a. That's why we found out what is the probability of capital A small a, which will be 2/3. But for 3 4 to be heterozygote, it is for sure heterozygote, right? Because mother has a small a allele that she has to give, and because 3 4 is not affected, so her genotype has one dominant allele. Okay, so 3 4 is heterozygote. So probability of 3 4 to be heterozygote becomes 1. Okay, so in the fourth generation, what is the probability of fourth generation to be, will have the trait mean to be homozygous recessive? So for that, it will be probability of 3 3 to be heterozygote multiplied with probability of 3 4 to be heterozygote. Okay, and multiplied with the probability that when 3 3 crosses with 3 4, they produce homozygous recessive. Okay, now the probability of 3 4 to be heterozygote, we have calculated it as 2/3. Probability of 3 3 to be heterozygote, sorry, 3 4 to be heterozygote is 1, and probability that their crossing will produce homozygous recessive is 1/4. Right, when two heterozygote crosses, chances of producing homozygous recessive is 1/4. So automatically you do the calculation, so this will come as 1/6. All right, so option 3 is incorrect. Answer is option 1. Okay, moving on to next question. We have 8 minutes only left. So everyone, please stay till the end of the webinar and the session, and you will all receive a surprise gift that will help you in your preparation. So actually, let me tell you the surprise gift also, so that you all can understand how helpful it will be. So there will be a set of 5 extra questions from previous year papers from Pedigree Analysis, along with its explanation. Okay, that will be given to you completely free if you stay till the end of the session. Yes, next one. So this is a pedigree chart given. The above pedigree shows the inheritance of a rare allele. So what is the inheritance pattern? That is what we have to find out. Okay, now in pedigree chart, whenever it is mentioning this rare allele, okay, so it actually means that this particular allele is present in few families in the population only. So basically what happens is anybody who is married into the family, okay, they will not be having that particular allele. Okay, but the individuals who are born in the family, they only have a chance of having the allele, but anybody who is married into the family for sure will not have the allele. Okay, right. Now, using that information, we have to analyze here. Right. So what we see, so if I'll just mark them all so that there is no confusion. So what we see here is 3-2 and 3-3 are affected, whereas nobody in the second generation is affected, and first generation indeed somebody is affected. Okay. Now this clearly is showing skipping of generation. Now, if you go by just skipping of generation, you will very quickly tick autosomal recessive, and that will become completely wrong. Okay, that is why this question is in CSIR exam. Okay, so to check your ability to differentiate between a probable answer and a correct answer. Okay, right. Now, what we have, like why it is not autosomal recessive? The answer is that autosomal recessive in this situation is possible only when both the parents are heterozygote. So when both the parents are heterozygote, then only there's a chance that they can produce homozygous recessive children. Okay. Now it is mentioned in the question that it is a rare allele. So 2-2 is not married in the family. 2-2, sorry, 2-2 is married into the family. 2-2 is not born in the family, right? So because 2-2 is coming from outside the general population, will 2-2 be having the causative allele? Not at all. Okay, which makes the genotype of 2-2 as capital A, capital A. If we say that it is autosomal recessive. Okay, now if 2-2 doesn't have the causative allele, in this situation, if we consider the trait to be autosomal recessive, will 3-2 and 3-2 and 3-3 have homozygous recessive genotype? No, not possible, right? So that's why autosomal recessive is not possible. Okay. Okay. Now, what will be the inheritance pattern now? So for that, what we see here, so 2-2 is coming from outside the population. So he will not have the causative allele. That means he cannot pass on the causative allele to the children. Okay. So if children have the trait, means children are getting it from mother only, because mother is the only one who is born in this family. Okay. Now, so basically these children, they are getting a single allele, maximum they are getting a single allele, because it is coming only from mother. Father can no way give this particular allele, right? So that means mother is passing the allele, and a single allele, even when it is present in 3-2 and 3-3, they are having the trait, the phenotype. Okay, so what it should be, what allele it should be, it must be a dominant allele, because a single allele is capable of showing its expression. So it must be a dominant allele. Correct? So it is dominant. All right. Now, if it is dominant, then ideally 2-1 should also produce the trait, right? Because she has the allele. Because if she is passing the allele to her children, means 2-1 also has the allele, right? But still 2-1 is not producing the phenotype. Reason is that it is not 100% penetrant. Okay, so dominant with incomplete penetrance, that will be the answer for this question. All right. So as you can see here, two things for pedigree analysis that you have to brush up. Actually, three things apart from the regular understanding of inheritance pattern. So you should know how to analyze a pedigree chart. Along with that, molecular markers extremely important. And as you can see that many questions are associated with complete or incomplete penetrance. Okay. So this concept of penetrance, if you are not confident with it, please brush it up now and start associating it with the pedigree analysis questions. Okay, so this way it will help you in solving the questions more easily and also correctly. All right, everyone. Okay, so I had some other questions also to solve. Okay, so this is one last question. Let's see before ending the session. So this is a pedigree chart given, and again you see these are information about the genes location. Okay, A, B, C, D genes. Which one of the following genotype is likely to represent a genotype of individual 2-1? Okay, now 2-1 is a female, right? Now the first thing that you should notice here is that 3-3 and 3-4 who are males, they are having only one copy of all the genes, whereas 3-1 and 3-2 who are females have two copies of all the genes. That means this four genes, or this line that it is showing, is actually a X chromosome. Right? So 3-3 and 3-4 who are males, who are sons, will get their X chromosome from whom? Only from mother. Right? So mother, for sure, you know that is giving A1, A2, B1, B2, C1, C2. Okay. And for D, you see that both are D1. So possibility is that mother can be homozygous for D1. Okay. But A, B, and C, for sure mother is heterozygous, because both the sons will for sure receive X chromosome only from their mother, and both the sons have A1, A2, B1, B2, and C1, C2 allele. Okay. Now see, with this information also, if you check the options, you have got your answer, because option 1 is showing homozygous for A2 and B1, and also for C2. Okay. So not possible. Option 2 is showing homozygous for A1. Again, not possible according to our finding. Option 3 is the only one which is showing heterozygous for A1, A, B, and C. Okay. But it is also showing heterozygous for D. But option 4 is showing homozygous for C. Okay. Which again is not possible. All right. So because there are four options and you have made sure that 1, 2, and 4 are not possible. So with this much information also, you know that your answer option 3 is the answer. Okay. Now, in case you want to check whether mother has D2 allele or not, so for that you have to check the females here, or the daughters. Okay. So daughters will get their X chromosome, one from father and one from mother. Okay. Now, because they have the same father, so the X chromosome coming from father will have the exact same linked gene format, right? So when you compare both the chromosomes, you see that A2B1 C2D1 is the chromosome which is exactly same. So this must be coming from father. Okay, which means the other chromosome here is coming from whom? From mother. Okay, and this particular chromosome that is there in 3-2 has a D2 allele, means mother has to be heterozygous for D as well. All right. So with this, answer becomes option 3. So that's all from my side, everyone. We have passed the time, although I had some extra questions as well for you, but we don't have. We have run the clock, and our time is over. So I have to stop the session, everyone. Before I go, there's one more time. I would like to tell you about the lecture batch, which is going to start from tomorrow. We have morning batch time as well as evening batch time. So if you need any further information, if you know somebody who needs information, who wants to join lecture batch, please dial this number, and with this enrollment you get the molecular biology hands-on training and internship program completely free. All right. Okay, thank you everyone for joining, and please don't forget to download the free document which has more questions on pedigree analysis along with the explanation. Please download that and practice those questions. Okay. So see you all again tomorrow with some other topic, and we'll be coming every day 6 to 7. See you all in this live sessions of Brahmastra series. Thank you everyone. Bye. Have a great day.